All right, if f is continuous on a to b, then the function, and we've seen this, capital F simply means the antiderivative. And don't read this as an equation, read it as these are equal to each other. These mean the same thing. That my integral on the right, the integral from a to x of f of t dt, is the same as the antiderivative of x. So this is an equation in a sense that these are equal to each other. Okay, so then the function has a derivative at every point x in the interval from a to b. And now this, so this is kind of some big, long, nasty notation, but it's really nothing that we can't handle. So d of capital F dx simply means we're taking the derivative of the antiderivative, which is the same thing as saying the derivative of our integral function. And when we look at this, I want you to be thinking kind of in your mind that d dx, it's taking the derivative of this integral. And we already know to evaluate an integral, we can use an antiderivative. And so that's why it's saying these first two pieces are the same. Because this is really, in parentheses, this is really capital F of x. So those first two pieces, the derivative of f with respect to x is exactly what it's saying here, d dx of f of x. But then the big piece is saying, well, that is equivalent to lowercase f of x. So if we take the derivative of an antiderivative, we kind of go full circle and we end up right back where we started. But I want to highlight the changes with variables as we go along. So this is part one of the fundamental theorem of calculus. All right. Now, this is very powerful. How they say when you take the derivative of the antiderivative, we arrive back at the same spot. Doesn't seem like much, but it does say that every continuous function f is the derivative of some other function. And I'm not going to test you on this. You're not going to be, like, AP won't ask for you to write this in words. This is kind of an FYI, kind of fills in what's going on. So every continuous function f is the derivative of some other function. And every continuous function has an antiderivative. So this is that connection again between integral calculus and differential calculus. And then the last thing, the process of integration and differentiation are inverses of one another. So I'll give you a minute to write this down, and this is just good to have in your notes. Like I said, I'm not going to quiz or test you on this, but this is good foundational information to be able to understand kind of what's going on. Okay. All right. So like this function, this notation can be intimidating, or we kind of glaze over it. I want to make sure that we really understand what's happening here. Okay, so I'm going to give you a little bit of the behind the scenes stuff that they imply with their notation, but I'm going to show it, spell it out, because for me, I mean, it took me a little bit to get this the first time I ever saw it. Okay, I was like, all right, I understand what it does, but I don't really understand it. I just know it equals f of x, and I would continue on. Okay, so we keep seeing this, but do we really understand how f of t dt becomes just f of x? Well, why that t change to an x? What's going on? I mean, I understand that that's the rule, that's the theorem. It's already been shown by somebody else, but is it really, do we understand what's going on? So I want to clarify that, like I said, I put it in parentheses. I use parentheses a lot if you guys haven't already gathered that. Like, I like to compartmentalize bits of information. I know, okay, that's what I'm working with there, that's what I'm working with here. So this is saying we're taking the derivative of this entire integral. Okay? And we've already talked, all right, integration is the same thing as anti-differentiation. And so if I had some function f of t dt, the antiderivative would be capital F of t. So we already know it's the antiderivative when I drop that integral symbol. And then I would evaluate at my bounds from a to x. But again, we're taking the derivative of all of that. Okay. This in my parentheses, it's going to get into part 2 of the fundamental theorem of calculus, but we can use this. We talked about this the other day. It'd be capital F of x minus capital A, or I'm sorry, capital F of A. So we know how to evaluate our antiderivative with the bounds. So I'm taking the derivative of this difference that I have going on. And so I could do, from my derivative rules, I could do each one of these individually. So it's the derivative with respect to x of capital F of x minus the derivative with respect to x of capital F of A. Back to our interval, a to x, a is a number. So it's going from some number to some unknown number. It's an interval when you think on the x-axis. Okay, say it's starting here at a, and it's going to some number x. We haven't defined what that is. It's just going out there somewhere. But a is defined. A is a number. So if I were to take the derivative of a number, that's 0. All right, that's some constant value. So I don't even have to worry about that. So all I'm left with is d dx of capital F of x. So if I wanted to take the derivative of an antiderivative, this now becomes lowercase f of x. So that's why it all equals just f of x, and there's nothing else going on with it. So that's how the t changed to an x based on our bounds, and then we use, which we'll officially call part 2 of the fundamental theorem of calculus, to actually show this. But this idea of taking a derivative of an antiderivative, I mean, that's kind of messes with your thinking a little bit to actually understand what's going on. Okay, so let's use that idea. Let's show that the derivative with respect to x, like I keep putting parentheses around this, but you will never see parentheses like in the problem given to you. They'll just write this as d dx, and they'll go right into the integral. If it helps you to put parentheses around it, do it. If it doesn't help, don't do it. I mean, it's just how I do it, and how I kind of compartmentalize. Okay, I'm taking the derivative of all of this. Okay, so I know my function in terms of t is t squared. Okay, how we were working with it before when it was just in that part 1 of the fundamental theorem of calculus is our integral of f of t. So in this case, our f of t is t squared. All right, so we're going to take the derivative of the antiderivative. So what's the antiderivative of t squared? So 1/3 t cubed. And we're going to evaluate that from 0 or I'm sorry, from a to x. And so we'd have 1/3 x cubed minus 1/3 a cubed. And again, we're taking the derivative of all of that. My derivative rules say I can break this apart, and so I can take the derivative of 1/3 x cubed minus the derivative of 1/3 a cubed. But again, a is a number, so the derivative of 1/3 a cubed, I'm taking the derivative of some number, this all goes to 0. So now my derivative with respect to x of my function 1/3 x is going to be just x squared. So that's showing that the derivative of a to x of t² dt is x squared. What gets trippy kind of working through these is we're doing antiderivatives and we're doing derivatives all within the same problem. So you have to keep it straight. Okay, am I anti-differentiating or am I taking the derivative? You have to be able to keep straight because you're going to be going back and forth on what you're doing. Okay, so this one, the derivative of this integral, this ends up being x squared. We probably see the connection that really this x was just going in place here at my t, and I've ended up with x squared. Yes, that's exactly what's happening. But I'm showing you the long way of what's going on in the background of why that's happening. Okay, because when I first started doing this, even back in college, I'm like, I don't really understand how it works, but I know x is going to go there, so it becomes x squared. Okay, let's do another one. So if I wanted to find the derivative of this integral, and this is simply applying that part 1 of the fundamental theorem of calculus, what is this going to equal? Simple as that. 1 over 1 plus x squared. Okay, so this is kind of the, not really shortcut, but this is what's happening. But the last 2 slides, I showed you why it's happening, what's going on. You don't have to take the antiderivative of this, evaluate your bounds from 0 to x, do all that work, because you're going to end up at this point anyway. That's what that fundamental theorem of calculus is telling us. Okay, so that big formula right here from the beginning, they're telling us that d dx of a to x f of t dt is f of x. Simply, instead of doing f of t, it becomes f of x. There's no anti-differentiation that you have to do. This is what the theorem says it is. Okay. All right. So let's talk now if we have a variable lower limit of integration. So say now they want us to find dy dx if our function is y equals our integral from x to 5 of 3t sine t dt. Okay, so first thing with integrals, we're always thinking from a number out. So a starting point and going out from there. Well, this one, we don't know that starting point, but we could rewrite this and I could change it up from 5 out to x of 3t sine t dt. How can I do that, Lena? Okay, I can change my bounds and bring a negative all the way to the left of that integral symbol. So you can change your bounds. And so now it's going from 5 to x of 3t sine t dt. It wants us to find dy dx. So what it's asking us to do is find the derivative with respect to x of each side. All right, so this introduces, when I'm doing the derivative with respect to x, this is how I get dy dx, and that's what they want me to find. They want me to find dy dx. And I'm going to take the derivative with respect to x of the integral. So what is the derivative with respect to x of our integral from 5 to x of 3t sine t? Louder? Okay. And so this one, it's okay because it's multiplication, but I'm going to write it out this way first. So negative of 3x sine of x. Or yes, you could write it as simply negative 3x sine of x. That is the derivative with respect to x of this function. Right? And it is that simple. You simply just put x in place of t. That's what the first theorem tells us. We can just put it right in. Yes, Jonathan. No, I haven't seen, not in this sense. No, I haven't seen any that say actually to prove it. But I think there's value in understanding what's going on behind the scenes. And I could tell you, I'm like, okay, yeah, all I gotta do is put the x in and go on. But we know what's going on behind the scenes. Okay. All right, so last one that we're going to do for part 1. So fundamental theorem of calculus, part 1 with composite functions. So composite function would be when we have more than one function going on. So we could say tangent of x squared. We know there's 2 functions going on, and we use chain rule, and we're going to work with chain rule again. So that's a composite function. You put one function inside of another. And now this additional function is in the form of an upper bound. So this does change things up. This is not as simple as just putting cosine x squared and being done. It's not that simple for these. And I'll show you that chain rule was happening in the other problems that we did, but we didn't even have to write it out. And you'll see why in a minute. Okay. So same setup, find dy dx. So we're going to take the derivative with respect to x of y, and then the derivative with respect to x of this, 1x squared cosine of t dt. Okay, in this one, the upper limit of integration is not simply x, now it's an x squared. And so again, that's why it makes y a composition of functions. And so this gets into kind of the theoretical part of calculus, that it's saying the upper bound is actually another function. And so it's hard to kind of picture, because we think of it as numbers. Okay, we're going along the x-axis. Well, now our upper bound is actually a function, so it changes things up a little bit. Okay, so let's identify our second function, x squared, and we're just going to call that u. And so we can write our initial problem now with bounds of 1 to u cosine of t dt, but then we would have to make sure we add in this piece that u is equal to x squared. So we can't forget about that. That's still part of the problem. We're going to have to use that. But we are going to change up our integral to just say it's 1 to u cosine of t dt. Okay. So now there's value in doing that. So now to find dy dx, we do have to use chain rule because it's a composition of functions. And just recall chain rule, this is that Leibniz notation. And we did talk about it like this when we were doing chain rule with derivatives. So the derivative of our function y with respect to u, so that would be the outside piece. Our function y, our inner function is some function u. But then the outside is our function, or the derivative of our function u. So the derivative of the outside, and then the derivative of the inside. So this is just a refresher on that Leibniz notation of the chain rule, still outside in. So in our case, the derivative of the function y with respect to u would be d du of our integral. Remember, our function y is that integral. Y equals our integral from 1 to u of cosine of t dt. So we're taking the derivative of y with respect to u, means d du of that integral, times du dx. Okay, all right. So what is the derivative with respect to u of our integral 1 to u cosine of t dt? Cosine of u. Simple as that. What is the derivative of u with respect to x? Okay, that's this piece up here, remember? U is x squared. So the derivative of u with respect to x is the derivative of this piece, which is just 2x. So therefore, getting back to, well, we're not done yet. Now let's take it, instead of saying cosine of u, we know u is x squared. So it'd be cosine of x squared times 2x. So the initial problem we were asked, what is dy dx when our y is our integral from 1 to x squared cosine of t dt is 2x cosine of x squared. That is the final answer. The first two example problems we did, when our bounds were from 1 to x, when it was simply a bound from 1 to x, or whatever the example problem was, du dx was still there, but the derivative of our bound of x was just 1. And so we were getting it where we were multiplying by 1, so we weren't even doing or writing out chain rule, but it was kind of happening in the background. We were just multiplying it by 1. Okay? But now when you have a bound that is not simply x, then we have to do a little bit more work. Okay? So this is as hard as the problems get, I feel, on fundamental theorem of calculus part 1, is when they have variable bounds, all we do, okay, we're going to recognize what that bound is, but we're going to change it to u, and then we're going to continue on with the problem. And this is a preview of what we're going to talk about next Tuesday, which is literally called u substitution, and there's different things we can do with it. So this is kind of a quick little preview of it, but we're going to have more complex integrals that we can work with, so we have to do a substitution. All right. Oh, no, this is the last part of part 1. And then part 2, I only have like 3 slides, and it's all one example problem. It's not, and it's not hard. Hopefully, this isn't kind of taking it here in these small steps. Hopefully, this isn't too bad yet either. But it's just kind of wrapping your brain around what's actually going on. So this one, construct a function with a given derivative and value. So they want us to create a function that's y equals, so y equals some integral, and they're telling us the derivative is tangent of x, but it also satisfies the condition that f of 3 equals 5. So I'll give you a second to write this down, and we'll jump into it. Okay, so they want our function to be in this form. So our final answer is going to be in this form, y equals, we're going to have an integral, we're going to have a function in terms of t dt plus some constant c. All right, they tell us dy dx is tangent of x and the condition that f of 3 equals 5. So f of 3 equals 5, what coordinates is that? 3, 5. All right, so my x is 3 and my y is 5. All right, so I want to be a function in this form, and it's going from a to some x value. So my only x value I know is 3. So I'm going to say 3 to some x value. All right, I wouldn't use the y there because remember, my interval is right along the x-axis. So I'm only thinking width. So I'm moving horizontally. So it's 3 to some x value. F of t, what would be my function in terms of t? Or what function am I working with? So it'd be what? Tangent what? Tangent of t. So we're working backwards. So we're trying to construct it. Tangent of t dt plus c. So we're off to a good start. So we know our function, which again our function represents the height of our rectangles. So the function is going to come from tangent of t. But now we need to figure out what c is. Well, I can now figure out exactly what c is because I know an x and I know a y. So my y is 5. My integral is from 3 to 3, tangent of t dt plus c. So I'm going to put in my x and y values that I know for sure. What's the integral from 3 to 3 tangent of t dt? 0. Okay, so that all goes to 0. So I end up with 5 equals c. So I know my constant is a 5. So final answer now, to write it out, would be y equals my integral from 3 to x, tangent of t, dt plus 5. That would be a function. If I were to take the derivative of it, I would get tangent of x, and it would pass through the point 3, 5. One thing that I want to point out here that you don't make the mistake, when we set this equal to 5 here in this step, do not think that we're bringing this over to the other side so it becomes negative 5. So we're not solving anything in terms of like an algebraic equation. What we're doing is we're recognizing that this is 0, so 5 is c, and so it stays positive 5. So do not treat this as an algebraic equation, bring that 5 over and think it's going to be negative. 5 is c. Okay, so that's the end of the part 1 fundamental theorem of calculus. All right, due Sunday by midnight, 23 questions. All right, let's talk about part 2. So part 2, we've already done stuff with. Part 2 is nothing. Part 2 is just kind of a nice piece to actually have a theorem that goes along with it. Starts out the same thing. If f is continuous at every point, and if capital F is an antiderivative of f, then to evaluate an integral, we simply take the antiderivative at B, subtract the antiderivative at A. This is what we've already done. And this is also called the integration or integral evaluation theorem. But now this is officially as a theorem. And what we were doing a couple days ago, we needed this to be able to answer it, to be able to evaluate those integrals. But now this is officially, this is the theorem. This is why it works. This has been proven that evaluating an integral is simply finding the antiderivative and plugging in your bounds. And what we've been working with are called definite integrals, and not before the test, but we're going to start to talk about indefinite integrals as well before this year is over. So definite integrals have bounds. All right, and we that's what the lesson was called. I think the last one we did was definite integrals. So definite integrals have bounds. Indefinite integrals do not have bounds. So we're going to get to a point where we don't have any bounds on there, and then there's more we can do with that. Okay, so that's the only slide I have for part 2 of the fundamental theorem of calculus. We've done enough examples. I think we feel good on that. We can do that. Now let's talk about area using antiderivatives. So we know an integral represents the area in relation to the curve in the x-axis. All right? So up to this point, when we were asked to integrate, we could figure out, okay, this is 5. That means the area is above the x-axis. My area is 5. If it became -5, I would think of it, okay, it's a negative of the area. This means the area is 5, but it's below the x-axis. What we can also think about is when we integrate, we're finding the area above the x-axis, so we treat that as a positive, and we combine that with addition with the area below the x-axis, okay? And so if I had an area above that was 5 and my area below was a -2, my integral, I would say, okay, the area is 3. Okay, on this interval, the combined areas of the two, take into account what's negative, what's positive, this would give me 3. And we'll call this a net area. Okay, it's taking all positives, taking negatives, combining them together, and spitting out one output. And so this is net area. So this is what an integral gives us. If you simply type in your integral from, in your calculator, you have an integral from 1 to 100, it's going to take everything above, everything below, it's going to combine it together and spit out one number. Now we can get more specific if they asked for a total area. So having a +5 and having a -3, I'm actually going to combine those without that negative sign. I'm going to say, all right, total area is 8. And if we want to look at total area, we can take our integrals and put them in absolute value with defined intervals. Okay, we're going to break up now. If our interval was from 1 to 10, well, I know 1 to 3 is above, from 3 to 7 is below, and from 7 to 10 is above. I would take that part that was below and I'd put it in absolute value bars because I want to know actually what number that is. I don't care that it's negative. I want to know the number, so I add up all those areas together. All right, so if they said find the total area, and they have to be specific when they ask you these problems, because if they simply ask for the area, that's not enough, because a regular integral will take a positive and a negative, combine them together, and just spit out one number. But if they say total area, they want to know, okay, how much is above, how much is below, let's combine those without thinking one's positive, one's negative, and get a big number for what it is. So find the total area of the region between the curve y equals 4 minus x squared and the x-axis when our x is between 0 and 3. So this is what our graph would look like. If we simply evaluated an integral from 0 to 3 of 4 minus x squared, it's going to take all of this positive up here, and it's going to combine it with the negative, and you're going to get an answer of 3. That would be the net area for this. Okay, it's going across that whole interval. It's taking the positive, it's combining it with that negative, and it's giving us 3 actually as an output. But if we wanted to find the total area, I want to take any of this down here, and I'm going to treat that as a positive. I want to know what that area is. I don't want to know the negative of the area. I want to actually know what it is. And so if I do absolute value of it, it makes it positive. So we need to look at each area individually and find the absolute value. So this interval, I'm going to split up from 0 to 2. And then combine that with my integral from 2 to 3. Okay, so my two actual integrals would look like this: 0 to 2 of 4 minus x squared dx. And I can put that right in my calculator and come up with a number. And I know that's going to be a positive value. And then I'm going to combine it with the interval or integral from 2 to 3 of 4 minus x squared dx. But we want total area. So fail-safe is always just put them both in absolute value. If you didn't graph the function or you don't have an idea what it looks like, without fail, just put them in absolute value bars. You won't have to worry about it. Okay. If you already have a graph and you know, well, I know this one on the left is always going to be positive. I mean, you don't have to put it in absolute value bars because you're getting a positive answer anyway. But then on the right, that is below the x-axis. If you simply put the absolute value bars and then do your integral all on the inside, do not do the absolute value of just this. Don't do that. Okay? It's not the absolute value of the function. It's the absolute value of the entire integral. All right? And so when we do this, we end up with 16 over 3 plus a positive 7 over 3 to end up with 23 over 3, which is approximately 7.67. So the total area, not taking into account the negative as a negative, is 7.67. But to make sure you cover all your bases, put each interval in absolute value, and you don't have to worry about it. Okay, so there'll be some questions if they say total area, or I mean, it'll be obvious when they word it. Okay, but I want to make you aware that a regular integral combines positive negatives and gives you like a net output. Well, if they want a total amount, and we'll get into some application problems in the coming week or so, where we do want to know that total amount, then we're going to work with absolute value. Okay, that's it. Easy enough, right? Still gave you plenty of time to work. My eyes were